You've seen those videos online, I'm sure, legged robots, uh, balancing, walking over rubble, even doing flips now. They're getting incredibly agile at just moving around.
Absolutely. But, the next big step, the real frontier, is getting them to actually do things once they get somewhere.
Right, especially tasks where they need to like physically touch the world,
Mm.
push things, manipulate objects.
Exactly. Think about opening a tricky door handle, or maybe wiping a surface gently, or even pushing something heavy. These aren't just about getting a hand to the right spot.
It's about the force, isn't it?
Yeah,
Applying the right amount.
precisely. You need to control how hard you're pushing or pulling and sense how the environment pushes back.
And controlling both that position and the force simultaneously.
Mm.
That sounds incredibly hard,
Oh, okay.
especially if you don't have dedicated force sensors everywhere.
That's the crux of it. It's a major hurdle because, traditional control methods and even a lot of the newer learning stuff, they often just focus on position. They miss that vital contact information.
Yeah, I can see that. And that lack of force sensing, it really limits how robots can learn from us, right? Like imitation learning.
Totally. A lot of imitation learning just records, the path someone takes, the trajectory.
Just the positions over time.
Right. But if the task needs contact, like wiping that surface with even pressure, just knowing the path isn't enough, the robot doesn't feel it, it might float above or press way too hard.
Okay, so how do you give a robot that sense of touch, the ability to control force, especially without the sensors? That's what we're diving into today, isn't it?
It is. We're looking at some really fascinating research that tackles this head on. They've developed a way to learn a single, unified control policy.
Unified, meaning it handles both.
Both force and position, yeah,
Yeah.
together. And the really clever bit, it learns to do this without needing those external force sensors.
Okay, I'm intrigued. So our mission for this deep dive is to unpack how this unified policy actually works.
Exactly. How it learns, what it can do, and, why this is potentially a really big deal for robots interacting out there in the real world.
All right, let's dig into the challenges first. Combining walking and manipulating is already complex, structurally. But what makes these contact-rich tasks so particularly difficult?
Well, the interesting thing is contact isn't just an obstacle. Often you need to control it very precisely.
You mean like compliant interaction?
Exactly that. The robot needs to act a bit like a spring, yielding gently when needed, pushing back appropriately. Think about placing something fragile down or engaging a spring-loaded latch.
Or even just bracing yourself while you do something else.
Right. You need to model and control those forces accurately.
And like you said, most robots just don't have force sensors covering their whole body, or even on their fingertips.
Precisely. That lack of direct measurement is a huge bottleneck. And it really explains why, as this research points out, just learning from position data falls short.
Like the blackboard example.
Yeah, if you only see the hand's path, you don't know the pressure. Is it actually touching? Is it scratching the surface? You just don't get that information.
Okay, problem defined. Need force control, lack force data, current methods struggle. So how does this research get around that? What's the core idea of this unified policy, and how does it manage without sensors?
So the main innovation is the single policy that integrates both position and force commands. But the real magic is how it figures out the forces.
Okay. If there are no sensors, how does it know? Is it estimating?
It's more than just estimating, it's inferring. It learns to do it. The policy looks at the robot's own internal state.
Like joint angles, velocities,
Yeah,
that kind of thing.
exactly. Joint positions, velocities, how the base is oriented, how fast it's moving. It takes all that history, that internal feedback.
And uses that to figure out the external forces acting on it.
Precisely. It's basically learning to read its own body language, you could say. How its own movement changes in response to interaction tells it about the force.
Ah, okay. So it gets this estimated force. Then what? How does it use that information?
It feeds that estimate back into its own control loop. It adjusts the position and velocity targets it's sending to the motors.
So if it feels a push, it can tweak its commands to either resist or yield.
That's the idea. It can compensate. If it needs to hold position, it adjusts to counteract the force. If it needs to apply a certain force or track an external one, it adjusts its targets to achieve that interaction.
That sounds a lot like impedance control concepts, doesn't it?
Mhm.
Making the robot behave like a programmable spring or damper.
It's definitely inspired by that, yeah. And because it learns this unified mapping, the policy becomes incredibly versatile.
So it can do simple positioning.
Yep, track a position. or apply a steady force, or even track a changing force, like if something is pushing against it. And it can do that compliant, springy behavior too, all from one policy.
Okay, learning to infer force from his own state and then using that to adjust. That's really clever. How do you actually train a system to do something that complex?
They used reinforcement learning, primarily. RL in a simulator.
Simulation makes sense. You need lots of trial and error.
Exactly. And not just any simulation. They used environments like Isaac Gym, which lets you run thousands, literally thousands, of simulations in parallel.
Right, that massive parallelism. Why is that so crucial for RL here?
Well, RL learns by trying things out and seeing what works, getting rewards. For a policy this complex, handling all these different forces and positions, you need an enormous amount of experience.
Just vast amounts of data.
Yeah. Running tons of simulations at once just speeds up that data collection incredibly. The policy gets to see way more scenarios much faster than you could ever do with a single robot or even a standard sim.
Did they just throw it in at the deep end? Make it learn everything at once? Position, force, disturbances?
No, they were smarter than that. They used a more structured two-stage approach, which often helps RL learn better.
How did that work?
First stage was about the basics, just learning to move, reach target positions, get the fundamentals down.
Okay, build a foundation.
Right. Then, in the second stage, they introduced the force stuff. Commanding forces, adding external pushes and pulls. They layered the complexity.
That makes sense.
Yeah.
And what was the overall goal during training? What was the policy actually trying to optimize?
It was trying to accurately follow whatever position and velocity commands it was given, while also reacting correctly to those external forces, matching that desired force position model.
And as part of doing that successfully?
It implicitly has to get good at estimating what those external forces actually are. That estimation becomes part of the learned skill.
All right, so the theory sounds good. Let's get to the results. How well did it actually perform, starting in the simulator?
In simulation, it looked pretty strong. For just tracking position, the error was typically quite small, like within 0.1 meters.
Okay, pretty accurate. And the force estimation itself?
Also quite good in sim, errors around maybe 0.05 meters in terms of positional effect. And crucially, even when they applied forces and the robot had to compensate.
Did the trekking get worse?
Not much. The position error generally stayed within that 0.1 meter range, so it showed it was effectively using that force estimate to stay on target.
Okay, sim results look promising, but the real world is always the big test. Did they measure actual forces on a physical robot?
They did, yeah. That's super important. They commanded the robot arm to apply different forces, up to about 60 newtons, and used a proper force sensor, a dynamometer, to measure what it actually produced.
But how close was the sensorless estimate?
The average errors were within 10 newtons, which is, pretty decent for not having a sensor directly measuring it.
Still, 10 newtons isn't zero. Was there a sim-to-real gap?
There was. They're quite open about that. They noted some larger errors along one particular axis, the y-axis, in the real robot tests compared to what they saw in simulation.
Any idea why that specific axis might have been off?
Oh, it's always tricky to pinpoint sim-to-real gaps perfectly. It could be subtle things, Maybe how the joints or motors behave in terms of friction or flexibility isn't perfectly matched in the sim.
Or just how contact physics works slightly differently.
Exactly. Things that might just show up more along one direction of movement than others.
Okay, so some real-world wrinkles, but still impressive. Now, one of the applications that really jumped out was using this to improve imitation learning. How did that work?
Yeah, this could be huge. Because, like we said, most robot demonstration data is just position.
It's a trajectory.
Right. If I guide a robot arm to screw in a bulb, it sees the path, but it doesn't learn how hard to push or twist or how to react if it gets stuck.
But this policy can estimate that force.
Exactly. So they use this policy during teleoperation. When a person guides the robot, the system doesn't just record the movement.
It also records the estimated forces the robot is feeling while being guided.
Bingo. You get force-aware demonstration data, richer data.
And did using that richer data actually make a difference when training other policies later?
A massive difference. When they train standard imitation learning policies using this force-aware data versus the position-only data, the success rate shot up. The source mentions something like a 39.5% average improvement across 4 really challenging real-world tasks.
Wow, nearly 40%. That's substantial. What were those tasks? They must have really needed that force sense.
They did. They were designed for it. First was wiping a blackboard needs smooth, consistent pressure. The position-only baseline only worked about 22% of the time, often floated or dug in.
And the force-aware one.
Much better. It could feel the contact, maintain pressure. Success rate jumped to 58%.
Okay, well,
Then opening and closing a cabinet. This one had a tricky push-to-open latch, needed just the right force over a tiny 3mm push.
hard to do with just vision, I imagine.
Very. Vision alone struggled. Baseline success was low, 36%, but the force-aware policy could feel when the latch engaged. Success rates were way up, 70% for opening, 72% for closing, and the last one involved occlusion, right?
Yeah, opening a drawer where the robot's gripper gets hidden from view as it pulls.
So vision fails you right when you need contact. Exactly. The vision-only policy often failed once it lost sight, only 30% success. But the force-aware policy could feel the handle, feel the pull, even when blind. Its success rate was 76%.
That really drives home the point that implicit sense of touch is critical for these tasks. So, beyond just making better training data, the policy itself showed off some cool skills directly, didn't it?
Oh, yeah, absolutely. They demonstrated its versatility. For direct force control, they had the robot hold up a 2.5-kilo dumbbell.
How much force is that?
About 25 newtons upwards. It just calculated the force needed and applied it. Clear force control.
Nice. What about tracking force?
They showed that too. They commanded 0 force. Then when someone pushed the robot's arm, it just yielded compliantly, followed the push.
Like a passive limb.
Kind of, yeah. And importantly, when the push stopped, the arm stayed in the new position because the command was still 0 force.
And the impedance control. The springy behavior.
They showed that mainly in simulation, things like simulated tug-of-war or arm wrestling, where the robot resists being pushed but proportionally to how far it's moved, really showing that compliant interaction.
And this wasn't just tailored to one specific robot model. It worked on different types.
That's right. They validated it on both a quadruped, a 4-legged robot, and a humanoid robot.
And for legged robots, force compensation isn't just about the arm. It affects the whole body.
Right.
Balance.
Exactly. For the base locomotion, compensating for force means adjusting the robot's base velocity, changing its stance or steps to maintain balance.
Does he show examples?
Yep. They showed the humanoid actually leaning its whole body to counteract an external push, staying balanced. And the quadruped, even when commanded to stand still, would take steps forward if it was kicked from behind, reacting to the force to stay upright. It shows the policy handles force for locomotion, too.
This is definitely impressive progress, a really significant step. But, like all research, there are limitations, areas to improve on. What did the researchers point out?
Yeah, they're clear about that. One thing is that the force estimation accuracy can sometimes dip a bit.
When does that happen?
Especially during really fast movements or interactions, or when the robot's joints are near their limits. They suggested maybe using velocity or acceleration data could help refine the estimates in those dynamic cases.
And that sim-to-real gap for force accuracy is still there.
It is. Getting that force control perfectly accurate in the real world, matching the sim across all conditions, is still a challenge. Those small differences in motors, friction, contact physics, they add up.
So more work needed on bridging that gap. Domain randomization, maybe?
Things like that, yeah. Or other sim-to-real techniques to make the transfer more robust.
And the current work focused mainly on force at a single point, right? Like the hand or the base.
Correct. Mostly focused on estimating the net force at the end effector for manipulation or the base for locomotion. But many real-world tasks are more complex.
You mean like pushing off a wall while opening something heavy?
Yeah.
Multiple contact points.
Exactly. Or using the whole body for leverage or support. Handling that kind of distributed multi-point contact is definitely a key next step for future work.
Okay, so wrapping this up, the big takeaway here is this really powerful new approach for legged robots to understand and physically interact with the world.
Right. By learning to control force and position together in this unified way, and crucially, learning to estimate those forces without needing dedicated sensors.
It's about giving them a much richer, more adaptable sense of touch, really.
Which should make them much more capable in complex, messy, contact-heavy situations, more robust, more human-like in their interactions.
And that side benefit of using it to create better training data for imitation learning, that could really accelerate progress across the board.
Absolutely. That alone is a huge contribution, potentially unlocking more complex skills much faster.
So thinking about those next steps you mentioned, particularly extending this to handle multi-point contact, whole body interaction, what does that future look like?
Well, that's a really interesting question, isn't it?
If a robot can truly master using its whole body, maybe bracing itself with its legs or torso while its hands do something delicate that requires force.
Hmm.
How does that fundamentally change what we can expect robots to do?
Imagine tasks in our homes, our workplaces, tasks that currently need that full body dexterity and physical understanding. What new possibilities open up when robots can interact with that level of physical intelligence? Something for you to think about.